Okay, so on Monday, what we did was, okay, first of all, we related this. We know that if we want to calculate S matrix elements, we had seen that LSZ reduction formula relates it to this n particle, so-called n particle endpoint function. And then we had shown with one shortcoming, I mean, there was a question mark over here I will first discuss. There is actually not a question mark. There was one point that I had missed in that discussion. But we had shown that that endpoint function can be this endpoint function of the full theory. It's the vacuum expectation value in the ground state of the full theory. You see, this omega just denotes the ground state of the full theory. It doesn't have to be the empty state. And these 5 fields are the solutions of the equations of motion of the full theory. They are the field operators. That's all the full theory. That we don't know how to calculate, but we managed to relate it to matrix elements in the empty state of so-called non-interacting fields. These fields that appear over here, they are evolved from some at t equal to minus, at some reference time, they are evolving under H0, the non-interacting theory. And so this was kind of one of our intermediate results, that the endpoint function of the full theory can be related to some function of the free theory with the states of the eigenstates of the free theory. And then we looked at how can we calculate various elements. And the idea is, since we have the vacuum matrix element between the empty states, if we can move annihilation operators to the right or the creation operators to the left, they will annihilate the state. We will get the commutators. The commutators are essentially the Feynman propagator. The commutators we will get will be nothing but the Feynman propagator. And so we will be able to evaluate every term in the expansion, in the evaluation of these matrix elements. Of course, in order to evaluate those, we have to expand the exponent over there. It will be an infinite expansion in the interaction. So if interaction is small in some sense, we can justify just terminating that infinite the many terms at some finite order, and we will be done. And then we looked at ways of simplifying this computation. So we started drawing all these diagrams, which are called the Feynman diagrams. And we were looking at the numerator. At least at the moment, the diagrams we are looking at look somewhat complicated. And this is where we had left. So any questions up to this point? So we will just pick it up from here and hopefully.
Can you just very briefly review going from one term to a diagram? So clear.
No, I will do that. I mean, today hopefully we will also finish the discussions of scalar fields. So next week your midterm will be about the scalar fields, and hopefully next week we will go to higher spin fields. Now, first let me just complete the missing part in our relation from matrix elements of the full theory to matrix elements of the non-interacting theory. How do we know that? How do we know this relation? If you remember, we had this UTT0. This is the evolution in the interaction picture, which we had written as e to the power minus IH t minus T0 e to the power IH0 t minus T0. Basically, this is the evolution in the Schrödinger picture of the state. And then we subtracted the evolution due to H0. What remains is, if anything remains, it will be an evolution of the state due to the potential. Then we said that if we have UTT0, UT prime T0, we had also shown that this is actually equal to the time-ordered exponent minus I from T0 to T dt prime Vi of T prime. We had said that this is equal to u of, this is the dagger, u of t prime, which is time-ordered exponent minus I from t prime to t, dt double prime, vi t double prime. Okay, these are things that we had used. Now, one mistake that I had made, this is not equal to e to power I h0 t minus t prime, e to power minus I h t minus t prime. They are not equal. That was the mistake I basically made. Because you see, in this expression, although t0 doesn't seem to appear, it is there in the definition of vi. So this definition of u is valid only if the second argument is t0, our reference time. I can still generalize it. I can take this u t prime for arbitrary t and t prime to be defined as this thing. Then this quantity would be e to power I h0 t minus t0, e to power minus I h t minus t0, e to power I h0 t prime minus t0, e to power minus I h t prime minus t0, dagger, e to power I h0 t minus t0, e to power minus I h t minus t0, e to power I h t prime minus t0. I just took the dagger of the second operator there. But this is, you see, I can combine these two exponents because the expression in the exponent commutes with each other, so I can just treat them as if they are just ordinary numbers. So I can combine those exponents. T minus t prime, e to power minus I h0, t prime minus t0. If you like, this is the evolution operator of my interaction picture state, not from the reference time t0 to some final time t, but from an arbitrary time t0 to an arbitrary time t. So what it does is, by multiplying with this exponent, it converts it into the Schrödinger picture state, then evolves the Schrödinger picture state, and then converts back to the interaction picture state. But if this is case, remember what we had was ut0 minus t acting on the vacuum. This was the state I had in my derivation. This is equal to e to power I h0 t minus t0, e to power minus I h t minus t prime, e to power minus I h0 t prime minus t0, where this t prime is actually minus t. Acting on the empty state, well, the empty state is an eigenstate of h0. You can fix the energy to be zero, energy of the empty state to be zero or some constant, but whatever, there will be some phase, depending on if you define the empty state to have zero energy with respect to h0, that phase would be just 1. Then you will get this quantity. Oh, sorry, another correction. T is t0. So this first term is just 1. This just acting on h0 will give me, acting on the empty state will just give me a phase. E to power minus I h t, that is t0. t0 plus t acting on the vacuum. Now I can use the adiabatic theorem. You see, 0 is the ground state at t equal to minus infinity. I am slowly turning on the interaction for a time t0 plus t, which is a very large time. eventually it's the full theory. After such a long time, the potential is fully turned on, so that after that time, my Hamiltonian is the full Hamiltonian of the system. Since I started from the ground state of my system at t equal to minus infinity, I made changes adiabatically, so my system always stayed in the ground state of whatever theory I have at that given time. So this state is just the Hamiltonian of the full theory with some possible phase. So u t0 minus t, of course, I'm always having in my mind that I'm eventually taking t to infinity. This is actually some phase multiplied by the ground state of the full theory. That was the missing link in my derivation on Monday. So this kind of completes all the missing links in our derivation. Yes, question? No. What? So if we go back, now we know that this quantity is equal to this matrix element e to the power I d4x. This is the interaction part of the Lagrangian. Oops, sorry. This is my result. Then we were, let's play with a different theory. I mean, I don't want to talk about the first kind of particle, second kind of particle. Let me change my theory to this one. At least it will be also another exercise in converting these matrix elements to diagrams. Let's take the phi to the 4 theory.
It's a real.
It's a real field. So the interaction Lagrangian is minus lambda phi to the 4. Now, I will divide this lambda by 4 factorial. I mean, it's completely arbitrary. You don't have to do that. But at least using the experience we had on Monday, I can see that these 4 factorials will be cancelled in almost all our derivations. Now let's look at the scattering of 2 particles. K1, K2 goes to P1, P2. I'm looking at this scattering. Well, a LSZ formula tells me that I can relate the S matrix element for this one to this.
It's eliminated because of the number of the Feynman diagrams.
Which one?
For factorial.
You will see in a moment. This scattering amplitude is related to this 4-point function. Let me just write it phi 1, phi 2, phi 3, phi 4. Phi I is basically phi evaluated at xi, x1, x2, x3, x4. So LSZ reduction tells me that I have to calculate this 4-point function. Now, we had just seen here, to calculate that 4-point function in the full theory, I can calculate this ratio in the free theory. I should calculate this one. Let's start with the numerator again. The numerator is This is equal to one plus I d4 x plus, let me also write the I squared over 2 factorial
We do this some statistical approach, just we don't have some continuous action in the hand, right?
Which statistical approach?
I mean, we are writing, numerator is the something normalization, and the denominator in the normalization, and the numerator is the something. We do this statistical physics, right? And
No, I'm not doing statistical physics over here. You see, here what is actually happening is when I take these limits, there are these factors n, which I don't know. You see, as I evolve the ground state adiabatically, it acquires some phase. That phase, I don't know what it is. But I know one thing. I know that this matrix element should be 1 when I don't have any phi fields inside the time-ordered product. So that tells me that this constant n should actually be equal to this number over here, whatever that number is. So that's what I'm doing here. I'm expressing everything, the unknown constants, which I don't really, well, I'm basically calculating n and putting it over there.
I understand.
Doing a normalization, basically.
Yeah.
It's normalized to 1, and that's why it looks like a probability, which is why you're thinking it looks like statistical.
Now, again, just although I didn't write it explicitly here, the phi's appearing on the left-hand side are full field, or are the fields of the full theory. The phi's that I write on the right-hand side are the fields of the non-interacting theory. They evolve under H0. The phi's on the left evolve under H. The phi's on the right evolve under H0. I'm just lazy to write all these indices, subscripts, superscripts. I'm just using the shorthand. Anyway, in all our computations, we will be dealing with fields of the non-interacting theory anyway, from now on, almost always. Well, let's start with the first one. Now, what we had done, if you remember our discussion, basically we need to move the annihilation operators to one side, the creation operators to the other side. Let's say that for the sake of argument, let's say T1 is larger than T2, larger than T3, larger than T4. So I will get 0. The time-ordered product will be just phi 1, phi 2, phi 3, phi 4, which will be 0, phi 1, the dagger operators, phi 1, the creation, the annihilation, the creation operators, the same thing for phi 2. This is what I have, if that is the time ordered thing. Now, phi 1 plus will annihilate the 0, so I can just drop it. So let me just look at this phi 1 minus. I have to commute it all the way to the other side. So I will get, now I have, let's say, phi 1 minus phi 2 plus. This is the commutator of phi 1 minus phi 2 plus phi 2 plus phi 1 minus. So when I commute this phi 1 minus towards the right, I get a contribution with the commutator. And between the phi 1 and phi 2 fields, multiply by this quantity.
I don't get it. The phi 1 and phi 2 is not commutative. I mean.
No, you remember phi 1 and phi 2, they are the same fields, just at different points, space-time
Okay.
points.
Okay.
Since if this was an equal time commutator, they would also commute. But this is no longer an equal time commutation. Equal time commutator. Remember, at equal times, only the field and the conjugate momenta, they don't commute. The commutator is non-zero. But at different times, all the commutators will be non-zero of the same field. And then I have plus. So if I use this expansion, I will get this term plus then phi 1 will be next to phi 3. I have to consider the commutator of phi 1 and phi 3. Phi 2 will stay where it is. And then I will have phi 4. Then I have the commutator of phi 1 and phi 4.
Shouldn't those commute because we are dealing with scalar fields?
Shouldn't?
I believe those commutators should commute because we are dealing with scalar fields.
Remember this one, phi r1 t, phi r2 t. This is equal to 0. But phi r1 t1, phi r2 t2 is not equal to 0.
Okay, so they are not different fields, but indices indicates pole position.
Yes, the indices, the phi 1, phi 2, you see, this is the definition I use. The indices just denote the space-time position. x1, x2, x3, x4. And since they are at different times in general, these fields will not commute. But you see, all these commutators are nothing but the propagators we calculated. What remains here, remember, this is our ordering. So these are already time ordered. All of these are also Feynman propagators. So what I do, this is what I want to calculate. Let me generalize it to arbitrary time. Whatever the ordering is, I will be commuting, if I start with phi 1, I will be commuting that with phi 2, phi 3, phi 4, etc., depending on the ordering of time. So let's say that, let me write the contribution that I get from commuting phi 1 and phi 2 by this line. And then there will be a commutation between phi 3 and phi 4. There is this contribution. There is this one, phi 1 will commute with phi 3. I will get the commutator of phi 1 and phi 3 and phi 2 and phi 4. And finally, I will commute phi 1 with phi 4. And I won't get any other terms because now the annihilation operator just moved. After this commutation, the phi annihilation operator moved all the way to the right, annihilating the empty state, and phi 2 and phi 4. All these these lines, so-called the contractions, corresponds to Feynman propagators. So at the end of the day, what I obtain is this time-ordered product is the Feynman propagator between x1, x2 and x3, x4 between x1, x3 x3, x4, the Feynman propagator x1, x4, x2, x3.
This is very clear.
Hmm? Yeah.
Okay.
I can show it diagrammatically. You see, I have these 4 points. Position them in whatever format you want. This is x1, this is x2, this is x3, this is x4. Well, here I have a propagator, in a sense, connecting x1 and x2. Let me show it by a line. This is a propagator connecting x3 and x4. Plus, I have 1, 2, 3, 4, a propagator connecting x1 and x3, another propagator connecting x3,
No,
sorry,
X2.
x2. That is x2 and x4. Plus I have the last one, one is connected to 4 and 2 is connected to 3. These are all, well, as you see, there is no scattering here, but this 4-point function in the non-interacting theory can be written as the sum of these 3 diagrams. Well, how do we calculate the diagrams? Well, each line, if you connected, if 2 dots, you connect them by a line, they will give you a Feynman propagator. So if you look at this term, it's just 2 lines. H1, there is a corresponding Feynman propagator, just multiply them. And this is what you get. You see, although we first calculated the mathematical expression, then draw the diagrams, later on we will draw the diagrams, which will be easier, and then from those diagrams, write down the mathematical expression. And if you look at this one, well, again, just 2 lines connecting 2 dots. Each line is a Feynman propagator, just multiply them. That is how we calculate a diagram. Let's go one, yes.
There is no any difference between those diagrams and we by writing this with tilt, right? It's when the 1 and 2 get interaction with each other and the 3 and 4 came out. But this, okay.
We will come to the interaction in a moment. Well, but let's do what the, you see, at lowest order, no interaction term, we just set L interaction to 0. What is the S matrix element? How can we calculate the S matrix element, the contribution to the S matrix elements from these diagrams? Well, we would expect 0. Remember what the LSZ reduction tells us. If you want to calculate the S matrix element, just apply this operator. There will be 4 of them. Apply these operators to your 4-point function. Take the Fourier transform. K1. K1 x1 d4 x2 e to power minus I k2 x2 d4 x3 e to power I p1 x3 and this is our LSZ reduction formula. The sign of the exponents determines whether it's the incoming or the outgoing particle. And this k1 squared, k2 squared, remember they are all m squared terms. Well, let me just look at this one. If I look at, let's say, the first term appearing over here, more or less the same thing will happen for all the other terms. The x2 is only in this Feynman propagator. Well, this Feynman propagator satisfies is the Green's function of that operator. So that is minus I Dirac delta 4 x1 minus x2. So that integral, let me ignore the factors, overall factors, is just e to the power minus I k2 x1. Remember, I act with this one, now I should act also with this operator. I have d4 x1 e to the power minus I k1 x1, x1 plus m squared e to the power minus I k2 x1, which will give me d4 x1 e to the power minus I k1 x1 minus k2 squared plus m squared, which is 0. Now the same thing will happen in all of them. If you act with one of them on some other diagram, that one will give you a Dirac delta, and the other integral will just give you 0. Now that is not a big surprise because there is no scattering here. Now, this was the first term in the expansion of the exponent. You see here, we have this expansion, we have calculated the contribution of 1. Now let's look at the other term. I d4 x lambda over 4 factorial phi to the phi x to the power 4. Well, what do I have? I have the point x1, the point x2, the point x3, and the point x4. And then I have the point x. There is one field at point x1, point x2, point x3, and point x4. Just one field. At the point x, I have 4 fields. Now, contracting fields basically means replacing them with the Feynman propagator, or in the diagram, replacing them by a line. So that means I have to connect all these lines together in all possible ways. Well, there are ways, let's say, I can connect 1 and 2, 3 and 4, and then I can connect these lines together. This is one possibility. Well, let's see. There is one possible contraction between 1 and 2, and one possible contraction between 3 and 4, but let me look at this phi x, phi x, phi x. Let me pick the first one. The first one I can contract with this one, the second phi, or the third phi. They are all the same. But I have 3 of the same. So that brings a factor 3. So that is something I have to keep in mind. And once I contract any 2, the other 2 is, there's no choice there. So let me write the corresponding factor. I have the Feynman propagator connecting x1 and x2. I have the Feynman propagator connecting x3 and x4. I have lambda over 4 factorial times I times 3, this 3 over here. And I have a Feynman propagator connecting x and x. I have a Feynman propagator connecting x and x. This is the contribution from this diagram. Well, what else do I have? Well, of course, instead of connecting 1 and 2, I could have connected 1 and 3, 2 and 4, etc. There are all those 3 possibilities. These are not that interesting. We will see what will happen to these, because there is just one part which we already calculated in the first order, 0th order in interaction, times something else that comes from the interaction. They are kind of separate. What will be more interesting will be terms like sorry, not this one. Let's say I connect 1 to one of these lines. Well, at the point x, there are 4 fields. I can connect the 1 to any one of these 4 fields. So they will all give me the same contribution. That brings a factor 4. I can connect this 3 to one of the remaining 3 fields. Again, any contraction with any one of the remaining 3 fields will give me the same contribution. So rather than calculating them one by one, I can just calculate 1 and multiply by 3. I can connect the field at the point 2 with one of the remaining 2 fields. Again, I have 2 options, two options that will give me the same contribution. And the 4 field will connect with one of them. So this is one diagram. Note that this is 4 factorial, which will cancel that 1 over 4 factorial in the definition of lambda. That is why I introduced that 4 factorial in defining that lambda. I don't have to do that, but conventionally we do that so that we don't need to worry about all those factorials in other places. Well, this is one other diagram. Here, what do I have? I have df x1 minus x, df x2 minus x, df x3 minus x, and df x4 minus x. I have a factor of I lambda over 4 factorial, which will cancel by this 4 factorial, so I just have I lambda. So this is just another diagram contributing to my process. And
There's one more. Yes.
well, there are several more. You see, another possible option is this one. You see, this, if I would draw it more properly, I would have this one. Here I have I lambda at this point. It will look nicer. Later on I will draw it in this form. Well, let's see. 1, 2, 3, and 4. I can contract 1 with one of these fields, 3 with one of these fields, 2 with 4, and then I have this loop. You see, when I'm connecting 1 to one of the fields at the point x, I have 4 options. When I'm connecting 3 to one of those points at x, I have 3 options. And there's no option left for the other 2. So I end up having I lambda over 2. In the first diagram, here I have, well, I have I lambda over 8.
Hocam,
four of these fields, at X, aren't they all same? How can I differentiate between those two? For example, the last diagram that you wrote, one goes, one of the four of them, but four of these, fields are the same.
Mhm. But if you go back to our discussion over here about taking one field and commuting it all the way around, I have to commute my field with each one of those fields at the point X separately.
If I don't have to, if they commute, then these calculations,
So I will get four contributions, four different commutations.
Okay.
But all of them will be identical because of the reason that you mentioned. They are the same. So the result, the contribution to whatever I am calculating will be the same. So because of that, we are just multiplying by these factors, because they will give the same contribution. But still, they will be separate terms because I have to commute my fields with each one of them separately.
So what's the difference between diagram 2 and 3? I thought what you were doing in 3 is what I thought you already did to do.
Well, diagram 3 is this one.
One to a field in the 5-4, and then
This is my second diagram. This is my...
okay.
Well, if I calculate the S matrix, this will not contribute because of this propagator, basically. Again, basically, we will have the same problem over here.
So basically, free propagator always kills the S matrix. A free propagator.
Well,
always
you see,
kills the S matrix.
what does the LS reduction does? Look at these terms. In fact, look at these operators. If you take somewhat do the integration by parts, what you obtain is k squared minus momentum squared minus m squared, which is 0. Right? The only way it will not be 0 is if I have 1 over p squared minus m squared in that term. So here I have 4 such terms, 4 such operators acting on my endpoint function. I should get terms with 4 poles, each corresponding to one of the external legs. So this one is just one pole corresponding to 2 of the external legs. So it will give me 0 when I multiply it with p squared minus m squared corresponding to both of those things.
Right.
This term will give me non-zero contribution because I have 4 terms. I have 4 different poles corresponding to each one of those legs, and in fact the contribution will be just this one. Well, let's calculate what the LS reduction formula gives me for that term. And by the way, of course, there are all the variations of this diagram. 1 connected to 3, 2 to 4, 1 to 4, 2 to 3. None of them will contribute to my S matrix element. There are all variations of this diagram. Instead of connecting 2 to 4, I can connect 2 to 1, 3, 4, and the other one has this bubble.
Is there any combination, difference between our 4 fields, legs of our şeyi atlayın. Bu dışarıda bizim yaptığımız dördüncü dereceden field'in içerisindeki onların bacakları arasında herhangi bir commutation alıyor muyuz biz? Hangisini seçtiğimiz? Mesela birle birleştirirken.
You have to consider all the possible combinations. You see, here I have all these 3 possibilities. Here, I was just lazy, and I just wrote the correction to this one. But there's exactly the same correction to this one, exactly the same correction to this one.
I know.
And you have to consider all of them, which means you have to consider all possible commutations between the external legs also. But any commutation between the external legs will just give me a propagator connecting the external legs that will not contribute to the S matrix. And I do a similar thing over here. In this diagram, what I do is basically this diagram is this one plus you add the bubble in one of those lines. You can add the bubble here. You can add the bubble here. You can consider these two lines, add a bubble here, another bubble here. You have all those options. I just draw one sample. You have to calculate all of them. But I already know that they will not contribute to my S matrix. So that is kind of gives us one of the rules to calculating the S matrix. We should only draw diagrams that are connected. You see, this diagram is made up of two separate parts. It's what we call a disconnected diagram. Disconnected diagrams do not contribute to our S matrix. In fact, it's to any order, they don't contribute to our S matrix. And this is a connected diagram. It's just one piece. Every part is connected to every other part. This is a disconnected diagram. Again, it won't contribute to the S matrix. And well, let's look at this term. Well, I say x1, x2, and x3, and x4, they all appear at different propagators. So let me just look at what this, applying this operator and taking the Fourier transform does to one of those propagators. So this will be, let's say, d4 x1 e to power minus I k1 x1 x1 plus m squared. Well, this is just a Dirac delta function. So this integral, with certain coefficients, will just give me e to power minus I k1 x1. Well, what will the other terms will give me? They will give me e to power minus I k1 x1, e to power minus I k2 x2, e to power I p1 x3, e to power I p2 x4.
x1
yerine x olmasın diye.
X, you are right. Times I lambda plus some factors from, there will be some i's over there, and we integrate over x. Why? Because you see the interaction contains that integral over x. And what will this give me? This is I lambda 2 pi to the 4 Dirac delta for k1 plus k2 minus p1 plus minus p2. Remember our definition of the S matrix. S matrix was well, there is the one which doesn't contribute. S matrix, we had defined it as I 2 pi to the 4 Dirac delta 4 delta p. This is the overall energy momentum conservation times what we called m. And we see that m is actually lambda at this order. So any questions? Let's give our 10-minute break and we will continue.
Hocam